Alright, welcome. In this video I'm going to go over the 2022-2023 MAT235 Term Test 3 solutions. Before I begin, I want to note that this test was more difficult, mostly in part due to the length, but also because of one Lagrange multiplier question that we'll definitely go over. But yeah, just keep that in mind if you do decide to take the test yourself for practice. It was longer than most tests were. The average wasn't significantly lower, but it was lower than the typical averages from the previous tests. So right here is the coverage. Again, term test 3 went over 14.6 to 15.4. 15.5 was not covered. Okay, first question. So this again, the multiple choice section. For this specific question, or actually no, that's for the next one. This one is a directional derivative question. So the question is we want to find the directional derivative of the function f of xy is equal to x squared y squared minus y cubed at a point in the direction of another point. So we'll first of all remind ourselves of the formula for the directional derivative. So we have, I'll write in a smaller pen. So du of f is equal to f sub x of x comma y times a plus f sub y of x comma y times b. Again, where a and b are the components of the unit vector u over here. So in this question, we need to compute a few things. We need to compute the partial derivatives of f with respect to x and y. We also need to find a unit vector as well in the corresponding direction of the question. So in this case, we have our points in this direction, so PQ. So PQ. And again, we can just subtract them component-wise. So we have -3 minus 1, so -4. And then we have 5 minus 2, so 3. Okay, so this is, again, the direction vector that our unit vector has to point in, but of course we have to find the unit vector now. So our unit vector, u, is equal to PQ divided by the magnitude of PQ. To compute the magnitude of PQ, I'll quickly do up here. But hopefully you do immediately see that it is 5. It's just Pythagorean theorem. So in this case, you have -4 squared plus 3 squared. Take the square root, which is again just the square root of 25, meaning your magnitude is equal to 5. So in this case, then, we know PQ, and we also know what the magnitude is, so we can just divide it out. So in this case, the unit vector is simply -4/5, comma 3/5. And of course, you can also verify this yourself if you do want to check. You can check the magnitude of this. It'll equal to 1. You can take my word for it, or you can check. Okay, next we need to compute the partial derivatives. In this case, hopefully you're already comfortable with it, with computing partial derivatives, so I'll just verbally go through it. So f sub x, or the partial derivative with respect to x, in this case, this is the only term containing x, so this goes to 0. In this case here, we have 2x and then times y squared, which is, again, we treat it as a constant. So we have 2x y squared times the first component of the unit vector, so -4/5, plus, and then now we're looking for the partial derivative with respect to y. In this case, both terms do contain y. So here, similar idea, we get 2y and then times x squared, or just 2x squared times y. And then over here, oh, it's a minus, okay, that's fine. So minus y cubed, so minus 3y squared. And then we have to multiply this by the y component of the unit vector, or the second component. It's times 3/5. And then now we can evaluate at our point. So again, this is our expression for the directional derivative. Now we need to, again, find it at this point right over here. So 1, 2. So don't use q. Q is, again, giving our direction. We're looking at the specific point here, 1, 2. So when x is 1, y is 2, this over here, we have 2 times 1 times 2 squared is 4. So we have 8, and then 8 times negative 4 is negative 32 over 5. And then over here, similar idea. So we have 2 times 1 squared is just 1 times 2 minus 3 times 2 times 2. So 3 times 4, so 12. Minus 12, so you have 4 minus 12. In this case, you'll have negative 8, and then you have negative 8 times 3, so negative 24. And then finally, you just add or subtract these, so you get negative, I believe, 56 over 5. I feel like I got a different number. Oh, no, it was negative 56. Okay, perfect. In this case, if you look at your options here, clearly none of them will match this. I don't have these off the top of my head, but some of these you can likely get if you do accidentally either use the incorrect point or if you compute the directional derivative incorrectly. You can get either of these options, but in this case, this is the precise directional derivative at that point, so we know it has to be none of the above in this case. So we'll write E here. All right. Next question, let f of x, y, z equal to x squared plus 2y squared plus 3z, and let S be the level surface given by this function over here. What is the normal vector of the tangent plane to this level surface at the points 1, 0, 0? In this case, again, let's remind ourselves of the tangent plane formula, or the equation. So we have f of x, y, z, I believe is how I expressed it, or yeah, so it's partial with this, times x minus x naught, and then f sub y, y minus y naught, and then finally f sub z of x, y, z times z minus z naught. Okay, so from this we can clearly see that as long as we're able to compute these partials over here, we can get the normal vector, which is again just reading off these parts over here. In this case, you can immediately see without even computing that you'll only be needing the partial derivative of f with respect to x, because we're evaluating at this point here, and they're all clearly separate, but I'll just show you each of them. So f sub x again is just 2x, f sub y is equal to 4y, and then f sub z is equal to 6z. Regardless, when you plug in sort of it being this point, obviously only this will matter, meaning your normal vector is simply just equal to 2, 0, 0, which means C is your correct choice here. Right, next question, find the center of mass of a lamina enclosed by the polar curve, r is equal to 1/2 cos of 2 theta for pi over 4, for theta between pi over 4 and 7 pi over 4 with constant density. So this right here is a pretty important part. This part here, symmetry, is also pretty important. So when I was doing this question myself, I completely choked on this question. I could not figure it out. But after seeing the solutions, it kind of made sense, and I'll try to explain it as clearly as possible. In this case, your best bet is to sketch first. So what that looks like is this. Hopefully that's enough room. So here you have, again, theta, and here you have r. This is where high school math comes in clutch, being able to graph this. So again, we know that our amplitude is 1/2, so our graph goes between 1/2 and negative 1/2. And then here we know that the coefficient in front of our theta value is 2, and so we can calculate the period. So we know again, period is equal to 2 pi over k, k being that value in front of theta, so 2 pi over 2, which is equal to pi. Meaning in this case, we can just graph cosine twice, but between 0 and pi for each each repetition of the cycle, or each cycle. So let's go over that. So we have pi over 4, pi over 2, 3 pi over 2, 3 pi over 4, sorry, 3 pi over 4, and then pi. So again, this is just the first half of our kind of unit circle, I guess you can think of it as. And then here we have 5 pi over 4. Let me move that over a bit. 3 pi over 2. And finally 7 pi over 4. Yes, 7 pi over 4, I think that's correct. Yes, okay. From here, we can now graph it out. Again, we know we're just simply graphing cosine, so we start at the max over here, and then we can proceed. Let's see if I can get a decent graph. Okay, honestly, not bad for a first try. I'm just going to keep this, and we'll work with it. Okay, so now we can sketch the polar graph, or the polar curve. Okay, now we need to keep in mind that we are graphing between pi over 4 and 7 pi over 4, but I'm still going to graph out the full thing just to show you where it comes from. But if it's outside of that range, I'm going to just draw it with dotted lines. So at 0, when again theta is equal to 0, we start at 1/2. So we start somewhere over here. And then from there, as we're sweeping through, once we get to 1 over 4, we hit 0. Meaning we have something like this. Okay, at 0, and then now our actual graph will start. So in this case at pi over 4, and then once we hit pi over 2, obviously we're going down, so we're reflecting it over effectively. So we have something like this. And at 3 pi over 4, sorry, at pi over 2, we need to hit negative 1/2. So meaning we're reflecting all the way down here. So that's how our graph goes to here. And then at 3 pi over 4, which is over here, we need to hit 0 again, meaning at this point over here. And then once we hit pi, we need to hit positive 1/2. So 1/2 again in length, so somewhere over there. And then at pi over 4, we need to hit 0 again, so right over there. And at 3 pi over 2, we need to hit negative 1/2. So again, 3 pi over 2 is over here. For negative, we have to go all the way back up here. That's a bit high. Maybe over there. Over here. And then once we hit, here, let me redraw that once more. You definitely don't need to be this accurate when actually doing it on your own, but I'm just doing it for the sake of completeness, I guess. That's what I always say. And then 7 pi over 4, somewhere over here. We need to again hit 0 again, so right over there. Okay. So something along these lines. I'm not actually sure if I butchered this. I may have, but it's fine if I did. And then from here, if you were to complete the graph, you would have that part again. So for now, we're focusing on this part over here. So this is where the constant density part is extremely important. If this was just any random lamina, the density will change throughout. But in this case, because it's constant, we're able to kind of get a visual or like a graphical center of mass. So in this case, we know y is between these two values over here, roughly speaking. So I'll draw that out over here. These are our y values, roughly speaking. And then x, again, because we're only focusing on this portion over here, we can say the center of mass, or actually I'll draw where x goes from first. So roughly there, and then again, you can obviously estimate where the middle of the x values are going to be, somewhere over here, middle of the y, so you can see that the center mass is going to be somewhere over here. Now, why is this helpful? Well, in this case, we can clearly conclude that our y value has to be positive, because again, it's on the center over here. Or y, sorry, not y is positive, y is just equal to 0. So that's something we know. And again, this is just kind of the moment about the y. moment about y, and then x, moment about x. In this case, again, we don't know much about it, but we know it must be negative. So x is not equal, but it's less than 0. So with this conclusion in mind then, all you really have to do is scour the options. So we know y has to equal to 0 first of all. So in this case, we know that, I'll use red. So A obviously can't be it, B cannot be it. C and D are the only prospects. Everything else is obviously incorrect because the y component is non-zero. Next, between C and D, you just need to find the one with a negative x component, which obviously is D in this case. So D would be your correct answer. I'll draw that back in black. So D is your correct option. Okay, yeah, this one again was a more difficult question. I personally definitely got it wrong. I think I almost tried actually evaluating the double integral. As you can see, based on the answer, it wouldn't have been very fun. But yeah. Okay, moving on. Question 2. For each part, write your final answer. Okay, so this is again just a short answer part. So part 1, or part I, suppose f of x, y is equal to e to the y times x squared. When x comma y is equal to 1 comma 2, find the unit vector which points in the direction of maximal increase of f. Okay, so let's just dissect that. That simply again means we're looking for the gradient of f. What you really want to pay attention to is this part over here, maximal increase versus decrease. Very subtle difference. The only difference is by a negative sign. I think I did the alternative test and they were asking for the maximal decrease, which I didn't pay attention to. You need to slap on a negative in front. But yeah, so again, we'll remind ourselves of the direction of maximal increase. This is simply just given by the gradient. So of f, simply just the gradient of f, or just del f. So let's compute that. So again, we have that del f. We know that this is just equal to f sub x, comma f sub y. And now we can compute this. So f sub x, again, x is a variable, e to the y we can treat as a constant, so this is just 2 e to the y times x, or 2x e to, yeah, 2x looks better. 2x e to the y. And then f sub y, again, y is a variable, derivative of e to the y is just e to the y, so just x squared e to the y. Squared e to the y. Okay, and then from here again we need to compute the gradient at this point over here. So yeah, I just wrote it as this. So del f, evaluate it at 1 comma 2. We can again just plug in 1 comma 2 over here. So here you have 2 times 1 times e to the power of 2, so 2e squared. And then over here, similar idea. We have 1 squared times e squared. So we have e to the power of 2. Yeah. And this right here is our gradient vector. So from there, we then need to convert this into a unit vector, again, because we are asked for the unit vector. So I will again write out the formula. Let's write it here just so I have enough space. So again, it's the vector itself at 1 comma 2, and this is divided by the magnitude of that same vector. So the magnitude we can compute on the side. Here, hopefully you see, because this is, you can see e squared is like a constant, you don't really need to include it, but for the sake of showing you the full computation, let's go over it. So we have our vector here, 2e squared, then e squared. And then we're going to divide this by the magnitude. So the magnitude I'll compute on the side really quickly here. Okay, magnitude of f at 1 comma 2. So again, we're just squaring each of these components and adding them. So I'm just going to write it out here. So 4e to the power of 4 plus e to the power 4, taking the square root of that. So here you get 5e to the power 4, or just root 5 e squared. Okay. From here we can proceed. So root 5 e squared. So here, this is what I meant. The e squareds will cancel out. So what you're then left with is just this. So you have 2 over root 5. And then here, this just becomes a 1. So you have 1 over root 5. And that right there is your unit vector. So I will just copy and paste that here. Perfect. Okay. Again, remember to keep in mind whether you're going in the maximal direction or the maximal increase or decrease. And then also remember you need a unit vector. Okay, next, let f of xy equal to sine of x plus y plus k times cosine of x plus y for some constant k in the real numbers. Find a value of k such that the function f of xy has a saddle point at the point 0, 0. If no such k exists, write do not exist, or D&E, or does not exist. So in this case, the immediate option or the immediate thing that should come to mind is just using the second derivative test. So as a reminder, that's d, that's f sub x times f sub y minus f sub xy squared. And in this case, we can now compute it. So to compute it, again, we need to obviously compute each of these parts over here. So let's do that right over here. So f sub x, again, we're taking x as a variable. Both of these do include x and y, so we'll take them, you can take them as you do normally. So here we have the derivative of sine. Again, it's just cosine, so cosine of x plus y. And then here, we're again taking the derivative of cos, so it's just negative sine, so minus k sine of x plus y. And then for f sub xx, we just take the derivative again with respect to x, so this becomes negative sine of x plus y. And then minus k times cosine of x plus y. Next, f sub y, very similar idea. I actually think it's identical, so yeah, pretty sure it is identical. So cosine of x plus y minus k sine of x plus y. Oops. And then f sub y, same idea, negative sine of x plus y minus k times cosine of x plus y. Okay, and then we also need f sub xy. So here you can take, we could do f sub yx again by Claro's theorem. We know they are equal or equivalent. But yeah, regardless, we can take this with respect to y instead, which again will give you the exact same answer as f sub xx or f sub y. So sine of x plus y minus k cos of x plus y. Okay, so now we can evaluate here. Before plugging it in, we can just evaluate it at 0, 0. So for each of these, you'll notice again, because they are all equivalent, I'll just evaluate it for one of them. If we plug in 0, 0 here, here I will write it over here. So f sub xx at 0, 0. This gives us negative sine of 0. So negative sine of 0, or let's write sine of 0. Yeah, I'll write brackets. Sine of 0 minus k times the cosine of 0 as well. In this case, we know again sine of 0 goes to 0, cos of 0 goes to 1, so we're left with negative k. From here, we can then plug this into our formula over here. So we effectively have negative k times negative k minus negative k squared which is equal to k squared minus k squared, which is equal to 0. And remember what the second derivative test tells us. Because it's equal to 0, we know that it is indeterminate or inconclusive, meaning it could be a local minimum, maximum, or a saddle point. We don't know. So in this case, yeah, again, it's indeterminate, meaning in this case it's D and E. Okay, last we want to consider the double integral right over here, where D is again the rectangle. I don't know why I keep saying again, but this is the rectangle. This again is your x, and this is your y. We're going to approximate the value of the double integral using 4 equal sized subrectangles and using the lower left corner of each subrectangle as a sample point. So let's get into that. And I'll just draw something that is relatively rectangular. So let's say this right here. Yeah, we can say that this is pi. This right here roughly is 2 pi. I think, yeah, we have our x values here and y values here. Okay, so here, okay, again, x between 0 and 2 pi, so we need 4 equal sized rectangles. We need to split the x into 2 and the y into 2 as well. So let's say all the way up here, this is pi, and then half of that is obviously just pi over 2. And now we can draw rectangles. So I'll try not to butcher that. Okay, that's not the worst. Pi over 2, it's probably a bit lower, maybe over there. Something like this. Okay, and again, this doesn't have to be super accurate. This is just for reference. Okay, so this is what this looks like. And again, we're looking for the lower left corners. So you can imagine this right here as one of them, meaning your corner would be here. Over here, corners over here. And then same idea for these two over here. So these 4 kind of X's that I've marked off, these are the corners of the lower left for each subrectangle, and they will constitute as our sample points. So now we can approximate this double integral. Okay, so I'll write it over here. So generally speaking, we know that our formula for the approximation is as such. So if m I is equal to 1, yeah, I'm really bad at drawing sigma, the sum, but that's fine. N j is equal to 1, and this is f of x sub I, y sub j, times change in a. We're again right over here, this part, oops, these parts over here, these are the sum of the functions evaluated at the sample points. And then this right here is the change in area, or just the area of one of the subrectangles. And again, for this, I'm not going to go too much into the intuition because I only have so much of it. If you do want to gain more intuition as to why we do this, again, it basically translates over Calc 1 concepts from kind of building up those small rectangles into kind of prisms, I guess. I'm not sure if that's what you want to call them, but again, there are better videos out there for that. For this specifically, I'm just going to go over the computations. So this, again, we can write equal to the points here. So we have these points over here. Do I need to label them? No, I'll just speak of them. So we'll start in the lower left corner over here, the very far lower left. So that's 0, 0. I'll write it in square brackets. So 0, 0. And then we'll just go clockwise, why not? So then this point over here, again, x is equal to pi, y is 0. So pi comma 0. Oh, that's theta, pi comma 0. And then up, we have pi comma pi over 2. And then finally, we have 0 comma pi over 2. Okay, but don't forget, we're also multiplying this by delta A, which is again just the area of one of the subrectangles. This length is pi, this is pi over 2, so you have pi squared over 2 as your area. So pi squared over 2. And then now we can just evaluate each of the inner points here. So f of 0, 0, in this case, again, this is this is the function we're looking at. So cos of 0 times cos of 0, it's just 1 times 1. And then f of pi comma 0, so cos of pi is negative 1, cos of 0 is 1, so negative 1. Oh, sorry, cos of pi, oh no, I did different points, okay, regardless. Pi comma 0, yeah, so cos of pi is negative 1, cos of 0 is 1, so you have negative 1. So negative 1 times 1. And then f of pi comma pi over 2. So cos of pi, again, is negative 1. Cos of pi over 2 is 0. And then finally 0 comma pi over 2. So cos of 0 is 1. And cos of pi over 2 is 0. This is again being multiplied by pi squared over 2. And then over here we can then compute. So as you see, this gives you 1 minus 1 plus 0 plus 0. So this entire inside bracket part is just equal to 0. So 0 times pi squared over 2, which obviously is just equal to 0. And that is your answer for this part over here. Okay, question 3. So let f of xy equal to x squared plus y squared plus x squared y plus 1. We want to find and classify all the critical points of f in R2. So let's get started with that. We remind ourselves of what it means for a point to be a critical point. It means as follows, so critical points. This again implies that f sub x and f sub y, they're both equal to 0, or 0. So obviously to proceed, we need to compute f sub x and f sub y. Partial derivative of f with respect to x is just 2x plus 2xy. And then partial derivative of f with respect to y is just 2y plus x squared. And now we can set them equal to 0. So f sub x equal to 0. We can factor out a 2x over here. So we get 2x times 1 plus y. And this is equal to 0. And then from here, we know that either x is equal to 0 or 1 plus y is equal to 0, meaning x is equal to 0 or y is equal to negative 1. And then for f sub y, that's equal to 0. We know that 2y plus x squared is equal to 0, meaning y is equal to negative 1/2 x squared. Okay, so now when determining the critical points, what you want to do is you want to pick either or, like just set when x is equal to 0, see what happens, and then when y is equal to negative 1, see what happens. Don't do them simultaneously. I'm thinking the logic behind this is they don't necessarily have to be these values at the same time. So just pick one, consider what happens, and then repeat for the other. So when x is equal to 0, we can now look over here. Obviously, y is also then equal to 0. And then when y is equal to negative 1, so we have negative 1 is equal to negative 1/2. So obviously, then x squared is equal to 2. Meaning that x is equal to plus or minus root 2. And then from here we can conclude that the critical points are as follows. So the critical points are, and again from our first case over here, we have 0 and 0. From over here we have x is plus or minus root 2, y is negative 1. So root 2 comma negative 1. And then finally negative root 2 comma 1, or comma negative 1, sorry. And these right here, yes, these right here are the critical points. But we're not quite done yet. We also do need to classify them. And in order to classify them, we need the second order derivative, or the second derivative test. So for that, we need to compute the second order derivatives. So f sub xx. Again, we can take a look over here, take the derivative of that with respect to x. It gives you 2 plus 2y, I believe. Yes, 2 plus 2y. F sub y. We can look over here. Taking this with respect to y, it just gives us 2. And then f sub xy. So it doesn't matter which one you take, just take it with the opposite partial derivative. So let's take this with respect to y. In this case, that would just give you 2x. Yes, 2x. And then now we can compute what d is equal to, which is our second derivative test. So again, as a reminder, f sub xx times f sub yy minus f sub xy squared. So after plugging this in, we get this times 2, so 4 plus 4y. And then minus 2x squared. So 2x in bracket squared, so minus 4x squared. Okay. Now, the next step is we need to evaluate this second derivative test at each of the points, the critical points. So d of 0, 0. So again, plugging in 0 and 0 into this formula. Here, this goes to 0, this goes to 0. So we know that it's just equal to 4, which is also greater than 0. With that in mind, we can also see the sign of f sub xx. It's also positive. So with that in mind, we know that whenever this is positive, we have either a local minimum or a maximum. The value or the sign of f sub xx will determine whether it's a local minimum or a maximum. In this case, because it's positive, you can always think of like concave up. So in this case, we know that this point is a, I guess, how did I write it? Yeah, so what the point is, so 0, 0 is a local minimum. Again, I remind myself by using this part over here, it's positive, so it has to be like a minimum down here. Okay, very good. And then d of root 2, negative 1. Root 2, negative 1, we can plug in over here. So 4 plus 4 times negative 1. Right, so this just goes to 0. And then you have negative 4 times root 2 squared, which is just a negative 8, I believe. Yes, negative 8. Negative 8. And again, by the second derivative test, we know that this is just a saddle point. So root 2, negative 1 is a saddle point. Next, for root 2 or negative root 2, negative 1, I'll just tell you that it's also equal to negative 8. You can again verify that, but you're squaring negative root 2, which will still give you 2, and then 2 times negative 4 will still give you your negative 8. This then tells you that root 2, negative 1 is again also a saddle point. Okay. Next part, we want to then find the absolute maximum and minimum values of f on the square region with vertices 1, negative 1, negative 1, 1, 1, 1, and negative 1, negative 1. So this is a very common type of question. Again, they'll give you some kind of region and they'll want you to find the absolute max and absolute minimum on that region. For this, hopefully the obvious first step for you is to sketch out the region. So we'll do that over here on the side. We'll draw a roughly square region. Yeah, close enough. So in this case, we'll mark down all the corners over here, and then we'll label them with the corresponding vertices. So 1, 1, 1, negative 1, negative 1, negative 1, and then negative 1, 1. Okay. Next, what you want to do is you want to consider the boundary now, because again, this part over here, the inner part, this is what we covered, up over here in this part over here, right? So this is again across all of our all of our 2. So we want to consider points on the boundaries now. What you also must keep in mind is that the absolute maximum and minimum can be anywhere, either on the boundary or within this region. So what that means is when we're looking in the specific region, you must consider any critical points that are within this region. And hopefully you see that this point 0, 0, it is indeed inside this region over here. It'd be obviously at this point over here. So when comparing all the points, you must also consider the value. In this case, it actually does become really important. But yeah. So then you want to label your boundaries somehow, some way. These are all linear lines, so it's convenient. Label this L1, L2, L3, and then L4. Again, you can call them whatever you want, but yeah. So first, we'll consider, so I guess you can also state this, but it's all not necessary. So by the extreme value theorem, you can say that the extrema exist. They do indeed exist. Okay, so from A, again, we'll keep in mind, so from part A, we have that, or I guess I didn't evaluate it, but we can evaluate each of these points over here. So, or only 0, 0, that's the only relevant one. So plugging in 0, 0 here, these all go to 0. Oops, these all go to 0. You're just left with a 1. So f of 0, 0 is again just equal to 1. And then now we can compute the maximum and minimum values along these lines over here. So for L1, or our first line over here, we need to find an expression for this line in terms of either x or y. It's a vertical line, so we know that this is just x is equal to something, x is equal to 1. So we have that x is equal to 1, and then I guess I wrote it twice, whatever, that's fine. X is equal to 1, and then you're going to plug this into your function here. So effectively what it looks like is f of 1 comma y, because again, you know that x is fixed at 1, or it's fixed to be 1. So you have f of 1 comma y, and then all you want to do is just to plug that in now. So you can imagine plugging 1 here, so you get 1 plus y squared plus y plus 1. So just y squared plus y plus 2. Y squared plus y plus 2. I believe, yes, okay. From here, there are some different strategies you can approach to find the minimum and maximum of a parabola. You can either use, I've seen the solutions taking the derivative somehow, but usually whenever I did it, I simply just completed the square in this case, which I'll just do over here. Yeah, so here we again just have y plus 1/2 squared. This part you don't even have to worry about because again, we're not really shifting it at all. We're just looking for the minimum and maximum values. But for this case, it's just minus 1/4. So 2 plus negative 1/4 will give you 7/4. Oh, voice crack. And then this is again on the certain interval. So for determining the interval, it's again between these two values of y. So -1 less than y less than 1. And then now you can just imagine optimizing this linear function, or not linear, but function of one variable. And in this case, this is simply a parabola that's shifted to the left. So you can sort of imagine something like this. But obviously you're only concerned with somewhere between here and here. So in this case, 1 would be the maximum and the, or not that point, but like the vertex coordinate would be the minimum. So you have -1/2 comma 1, I believe. Yes, so -1/2 here would be the minimum, I believe. Yes. Yeah. So f, and then again, x is fixed to be 1. Y, the minimum value, we'll just evaluate both. Okay, yeah, in this case, you can directly look over here and evaluate. So whenever you plug in y is equal to this, x is again fixed, which is why we're able to use this. We know this just gives us 7/4. And then we, again here, we'll label this as the minimum. and then f of 1 comma and then 1, I believe. Yes, 1 comma 1. And again, this is, you can again imagine graphing it out. You have like a minimum here, this is like -1, this is 1 here, so the bottom of the parabola at -1/2 would be the minimum, and this point here on that interval would be your maximum. So then plugging this in over here, you have 1 plus 1 plus 1 plus 1, so just 4. And this right here would be a maximum. Again, not the global or not the absolute, but this is just for this interval along L1 or our first line. Let me see if I missed anything. No, we're good. All right, L2, very similar idea, except in this case we have a horizontal line, meaning you have y is equal to 1. So you plug it in a very similar manner, so f of x comma 1. You can go up here. So f of x comma 1. So we have x squared plus 1 plus x squared plus 1, which is just 2x squared plus 2, which we can factor out the 2 to get 2 times x squared plus 1. Okay, so I'll just write it, yeah, 2x squared plus 2. And then, okay, I guess I did use their derivative strategy. I'll show how that works, I guess. So we have, this is on, again, x is between -1 and 1, because if we look over here, this line over here, it's effectively bounded by those two values over here. So if we take d over dx, so yeah, so d over dx of this function over here is just equal to 4x. And we set this equal to 0, meaning that x is equal to 0. So this is how you can tell that, again, x is equal to 0 would be your minimum on this interval. You could also just recognize that this right over here is an unshifted or untranslated in terms of left and right, which means that the vertex coordinate isn't affected, meaning you just have a standard parabola that's kind of translated and stretched a bit, but regardless, the vertex still stays the same at 0. So that's how you can verify that. Okay, x is equal to 0. That again is our minimum value. On this interval then, over here, we know that either -1 or 1 both work. So here we have, for the minimum, f of 0, comma 1, meaning we just plug in x is equal to 0 here and we get 2. I believe 2. Yes, 2. Okay, and then here we can evaluate either at -1 or 1. Doesn't matter. I'll just do it at 1. So f of 1 comma 1. Again, if you plug that in here, you just get 4. So on this interval, this would be your min, this would be your max. Okay, and then let's go to L3. So for L3, we have x is equal to -1 now. Meaning you again have f of -1 comma y. Let's see what that's equal to. So f of -1 comma y. So you have -1 squared, so 1, plus y squared plus 1 times y, so plus y plus 1. So again, you have the same thing as previously. We've either L1, I think it was L1, plus y plus 2. So in this case, we can, yeah, let's write it out here. So y squared plus y plus 2, meaning you get the same thing here as L1. I believe that, L1. Okay, L4, let's see if this one was any different. So L4, we have y is equal to -1. So we have f of x comma -1 of x comma -1. So again, -1 here, so you have x squared plus 1 plus x squared times -1 plus 1. So in this case, these two would cancel out, so you're left with a 2. So in this case, it's just constant on this interval, 2. Okay. From here, you can then take a look at all the values that you do have In this case, we are looking for an absolute max or a minimum. If you scour all the points we have over here, clearly this right here, f of 1 comma 1 or even negative 1 comma 1 will give you a maximum. For the minimum value, you may be tempted to either use 2 or 7 over 4, but you do need to keep in mind that we also have this right over here. Very, very common mistake to forget about this, but again, this is in this square region over there. So we can then write a conclusion now. So we can say, thus, the absolute max is, and again, we can just write one of the points. So f of 1 comma 1, which is equal to 4, and then the absolute min is f of 0 comma 0, which is simply just equal to 1. So again, must be careful with remembering that a point can be still on that interval even if it's not along the boundary. So whenever you have a region like this, your absolute max or min can either be on the boundary or within the region, which is again why you need part A, which gives you exactly that. Okay, question 4. The base of an aquarium with given volume V is greater than 0, important detail right here, is made of slate and the sides of the aquarium are made of glass. If slate costs 5 times as much per unit area as glass, use the method of Lagrange multipliers to find the dimensions of the aquarium that maximize the total cost of the materials. Okay, so yeah, obviously we can assume the global minimum exists. This right here is a detail we want to keep in mind. So what they didn't mention in the question is that this is a box with no lid. So this here, box with no lid. Okay, so we'll begin by drawing a quick sketch. So we have something like this. Again, just a very rough sketch. So something like this, and again, no top portion. This we can call X, Y, Z. So yeah, so here we can call X the length. Then we can call Y the width. And then Z, obviously the height. Okay, I'm also going to preface this question by saying that I also didn't get this correct on this midterm. This one was one of the more difficult questions, and most of that comes from the fact that there is no kind of surefire way of solving the problem. You kind of just have to rely on some intuition. There's, again, no real kind of set out way to do it. There's only some strategies that you can try your best with. Okay. What else? What other things we need to keep in mind is that V again is greater than 0, as I keep mentioning. And that is because that also means that X, Y, and Z, they all must be greater than 0. And obviously that's kind of a natural constraint just because, again, length, width, and height are usually all greater than 0. Okay. So first, we're looking at the cost function, and one of the things I confused for some reason was the actual setup itself, which is usually always the confusing part, so I'll try to clarify that over here. So here we have the cost function. And I'll just underline this in red here. It's the cost function, and again, we can just call this F, so F of X, Y, Z. So we can now just think of the cost in arbitrary terms. So let's see, yeah, so exactly. So we have, it's made of slate and the sides are made of glass. And again, slate costs 5 times as much. So yeah, the base. So the base, again, is just X times Y. So obviously 5 times X times Y will give you the base portion of things. And then you have all the sides now. So this face right over here and this face right over here, obviously these are X times Z. So we have 2 times XZ, 2 times XZ. And then we also have that face and that face right over there. These are both Y by Z, so plus 2YZ. Okay. With these in mind now, we also do need to keep in mind the constraint as well, which is, yeah, so and then we have the constraint function here, so constraint. In this case, the constraint function is simply just x, y, z is equal to whatever the volume is, v, yeah, and v, and we're given that v is also greater than 0. So this is again where the unambiguous, the unintuitive part, that's kind of where it comes in. I personally was confused by this, but for this part, I'm just going to go off of their solutions. So as usual with Lagrange multipliers, we have that the gradients are equal to each other up to some scalar. So I guess here, yeah, we should call this g. Yeah, here we'll call this g right over here. So g of x, y, z. Is equal to v. And then this is where now we can use Lagrange multipliers, which is again that concept of the gradients being equal to each other up to a scalar. So first we'll compute the gradient of f, or just del f. So again, f we have right over here. So we're computing the partial derivative with respect to x first. Let me make that with x. So when x is a variable, we have 5y. Then plus 2z. And then, yeah, x is a variable, so that's it. And then now y is a variable. So again, looking over here, y is a variable, so we have 5x. And then for the second part over here, this just goes to 0 because there's no y involved. And here the y goes to 1, so we're just left with 2z. And then finally, with respect to z, here this goes to 0. Here we're left with 2x. Here we have 2y. So 2x plus 2y. And that right there is the gradient of f. Just making sure 5y, 2z, 5x, 2z, 2x, 2y. Very good. And then we also need the gradient of g, or del g. So right here, x, y, z, or z. This one's simpler with respect to x. It's just yz. With respect to y, it's just xz. And with respect to z, it's just xy. Okay. With this in mind now, we can now use the method of Lagrange multipliers, which generally just looks like this. So you have that the gradient of f is equal to some scalar, usually lambda, times the gradient of g. And if you do have an extra constraint function like h, you would just call the scalar, I guess, mu instead right after, but for now we'll just deal with this. Okay. So if we're equating these, we know that we're simply just multiplying each of these by lambda and then equating it component-wise. So we then have the following system. So the system, so again, equating things component-wise, but then multiplying g, or del g, by lambda. So you have 5y plus 2z. I'll write them one, so 5y plus 2z. And this is equal to lambda times yz. Two, we have 5x plus 2z. This is equal to lambda xz. 3, we have 2x plus 2y. This is equal to lambda times xy. Okay, and then finally, as a fourth constraint, we just have the function g itself, which is that x, y, z has to equal to some constant v. Okay, so this is where the unintuitive part will come in. Usually, again, your goal is to simply solve for x, y, z. And depending on the constraints of the question itself, you can sometimes conclude that, let's say, lambda cannot equal to 0 or lambda must equal to something. But yeah, so in this case, we're going to first use 1 and 2. So from 1 and 2, we have as follows. So we can isolate for lambda in each case. Yeah, so how do we want to do this? Yeah, so we'll divide both sides here by yz in order to isolate. So what that then gives us is, so from 1, we have, yeah, I'll write out the full way. So we have 5y plus 2z is equal to lambda yz. And then when you divide both sides by yz, you then get that lambda is equal to 5 over z plus 2 over y. Okay. And then, do I have enough space for 2? Yeah, I should have enough space for 2 here as well. And then from number 2, very similar idea, except we're dividing both sides by xz now. So you have 5x plus 2z is equal to lambda xz. Dividing both sides by xz then gives you that you have 5 over z plus 2 over x. This is equal to lambda, or lambda is equal to that, same idea. From here, we see that we have lambda written as these expressions here, so we can then equate them. So we then have 5 over z plus 2 over y. We know that this is equal to 5 over z plus 2 over x. And again, we're allowed to assume all of this, again, because x, y, and z are all greater than 0, so we're able to manipulate and move things around like this. From here now, we can see that these cancel out, and we're left with 2 over y is equal to 2 over z. Sorry, 2 over y is equal to 2 over x. And from this, we can then conclude that x must be equal to y. All right, so this right here is one of our main components of solving the entire question. Next, we want to use number 3, or the third condition. We are reaching the bottom quite quickly. Let's see if I can move this over a bit. There we go. Okay. So now from number 3, we have the following. Okay, similar idea. So we start by dividing, where's number 3? So we start by, again, dividing both sides by xy. So 2x plus 2y is equal to lambda xy, yep. And then now we can divide both sides by xy, meaning we have lambda, and then 2x divided by xy is just 2 over y, and then 2y divided by xy is just 2 over x. Okay. And then here, because we have x is equal to y, we can make direct use of that, meaning that this is equal to 2 over y plus 2 over y, which of course is just equal to 4 over y, I believe. Yes, 4 over y. All right, so this is again solving and seeing that lambda is equal to 4 over y. And then now we can plug this into either of these expressions. I believe they use the first one. So I'm going to label this a star. So say star, and we plug this into, so we plug this into 1. Yeah, we'll plug it into 1. 1 being this expression right over here. So we plug this value of lambda in. We then see that we have 4 over y is equal to 5 over z plus 2 over y. So over y. Okay, and then now our goal is to simply solve for z in terms of y. Okay, and in this case, we can do so however we see fit. So let's see if we can multiply. Yeah, we'll multiply both sides by y first. So you have 4, and this is equal to 5y plus 2. Or sorry, you have 5y over z plus 2. Multiply both sides by z. You have, or here, we can first add over or move over the 2. So you have 2 is equal to 5y over z, meaning then that z, and again we just multiply the z over and divide by 2. So we have z is equal to 5 over 2y. I believe, and then of course because x is equal to y, this is also equal to 5 over 2x as well. And then from here, we can make use of the constraint function right over here, or condition number 4, same idea. So from 4, I believe, yeah, we then have as follows. So v is equal to, again, x, y, z. And then because x is equal to y, we can write this as x times z times z. But then z, we also have an expression in terms of x, so times 5 over 2x. And then this gives us that v here is equal to 5 over 2x cubed, which then also means that x here is equal to 2 over 5v. And then we cube root that. So cube roots, and then similar idea here for y. We know that x is again equal to y, meaning we have this expression again. So therefore y is also equal to 2 over 5v cube rooted. And then z we have as an expression of either x or y. So we can write it as such. And z, so 5 over 2y, 5 over 2x, same idea. So just 5 over 2 times this expression over here. Cube rooted. And this would be your final answer here. So x, y, and z. Again, admittedly, so this question is quite confusing, even for me. I can't say I'm fully reading off the solutions, but this is the idea. You again use Lagrange multipliers, and off of this equality over here, you then try to find what x, y, and z can be. In this case, they did it through lambda. In other cases, you may not need to do so. In this case, that was one of the ways. I'm sure there's another way out there that doesn't involve this, but this question itself was kind of not poorly worded per se, but we definitely weren't prepared for it based off of the practice questions that we were given. Most of them didn't deal with this kind of scenario where, again, the costs and the constraints were a bit ambiguous in my opinion, because this isn't like exactly what we're used to, but that's kind of natural for term tests. Yeah. Question 5, find the volume of the solid bounded by the cylinder x squared plus y squared is equal to 4, and the planes z is equal to 0 and x plus z is equal to 4. So with this type of question, usually what you want to do is sketch it out first. I think when I was doing it myself on the term test, I didn't. I was just kind of visualizing what it looked like and then going off of that. But usually your best bet is to draw a sketch. So that's what I will attempt to do over here. So these are your axes. So here you have your x, y, and z. Let's label them like this, okay? And then first we want to sketch the cylinder part. So again, it's not going to be the scale, but this is roughly what it'll look like. Maybe a little water out. Yeah, something like this. And then, yeah, this is pretty poor drawing, I'm not going to lie. And then go up. Okay, definitely don't judge me on the sketching skills here, but regardless, this is your cylinder, and then z is equal to 0, we don't have to draw it, it's just the xy plane, and then x plus z is equal to 4. We can first rewrite this here as z is equal to 4 minus x, which actually turns out to be the function we're integrating over. Because again, in this situation, we want to find a function of x to integrate. Regardless, we can also sketch this out to see what it looks like. Hopefully you do recognize that it is indeed a plane. What you can do is you can focus on the xz kind of axes here. If you set z equal to 0, you know x is equal to 4. So let's say somewhere over here, roughly, because you know this right here is equal to 2, so this is roughly equal to 4. And then similar idea, x is equal to 0. We know that z is equal to 4. So let's say somewhere over here. So what you'll then get is something like this. So basically a plane. I'm going to erase these two lines over here. But it's basically a plane, which I'm now realizing is not that well drawn here. Let me draw that again. Okay, something like this. Obviously, again, please don't judge my artistic abilities. What this actually really becomes is you can imagine a cylinder, just like a cylinder, and it's kind of being sliced diagonally. So what the shape ends up looking like is something like this. So we draw the base, and then it's effectively cut off. So, okay, that's it's still not great, but something along these lines. Basically, you have a cylinder, and then it's kind of being sliced in half, and that's kind of the situation that's going on. So in this case now, we want to then basically find the projection into the xy axis in order to actually integrate this. So in this case, we will sketch out the xy plane. So this is the strategy you usually want to go with. You usually want to sketch out the coordinate planes, or whichever kind of planes that you are projecting into or dealing with. So this is again the x and the y. In this case, we only just have a circle of radius 2. Be careful. This is, again, x squared plus y squared is equal to r squared, meaning what r squared is equal to 4, so obviously r has equal to 2. So you have a radius circle of radius 2. 2, negative 2, negative 2. In this case, I have a tool that does draw the circle for me, so we're going to be better off here. Okay, roughly in this shape, you get the idea. Okay, and then now we do also want to, I guess, represent this region or find a set D that represents it. So we'll just use this over here. So this is again our region D, and it's a circle. So your first immediate choice should just be polar coordinates, because again, it's very awkward if you do try to just use Cartesian coordinates. Obviously you could if you just bound this between -2 and 2 for x, and then y, you can solve for y. You get like y squared is equal to 4 minus x squared, and then you have to take the plus or minus square root. It basically just gets really messy. So we'll use polar coordinates, and again we can represent this using r and theta. R theta, such that our radius is again just between 0 and 2. And then this one, so radius, because again we're looking at this entire region, right? So we have r is between 0 and 2. Theta, on the other hand, it's the entire circle, so of course we need 0 and 2 pi, so 0 less than theta less than or equal to 2 pi, just like that. And now we have our region. So from there we can actually find the volume now. And we can find it as follows. So we have volume. We'll write it in the general form over, it's like integral and then dA, which gives you kind of the general, or just the double integral over a region. And then we're going to convert to polar coordinates. So you have the double integral over d. And again, the function we're integrating, we need a function of, so z is equal to something in terms of x and y. In this case, y doesn't appear, which is fine. But this right here is the function we're integrating over. So 4 minus x, and then dA. And now we can convert to polar coordinates. So Here, again, remember polar coordinates. When we're integrating with the double integral, it becomes r dr d theta. So theta is on the outside, meaning we need to write theta first. So 0, 2 pi. Theta goes between 0 and 2 pi. And then our radius goes just between 0 and 2. And then we have 4 minus x, but again, remember x in polar coordinates, we have r cos theta. And then, of course, do not forget the r dr d theta. Dr d theta. So when converting to spherical coordinates, again, remember, or when we're integrating at least, doing this change of variables, we need to multiply by this r. And later on, I'll definitely have a video on this, but it has to do with change of variables in multivariable, just with multivariable functions. And it's very similar to a u substitution, I believe, but obviously more complicated. It involves something called the Jacobian, which I'll definitely also have videos on eventually. Okay, simplifying this, we then get integral 0 to 2 pi, then integral between 0 and 2. So now we can just expand this. So we have 4r minus r squared cos theta, and then dr d theta. Next, we'll integrate now, clearly with respect to y, or not y, but with respect to r first. So again, 0 to 2 pi still stays. And then here, derivative of what is equal to 4r. We know it's just 2r squared. And then same idea, but this time just with r cubed. And then cos of theta. This is being evaluated now. You can just write 0 and 2. It's usually what I do, but you can also write r is equal to 0 and r is equal to 2. If you do find yourself forgetting, or if you find this helpful, to again remind yourself what you're plugging in here, again using FTC, fundamental theorem of calculus. And then we just evaluate that. So we have integral 0 and 2 pi. Oops. And then we just plug this in now. So for r is equal to 2, we can plug in. So we get 2 times 2 times 2, so 8. And then r cubed is also 8, so minus 8 over 3 cos theta. And then we could subtract off when you substitute r is equal to 0 in, but of course you'll notice that they both contain an r term, meaning it just goes to 0. d theta. And we could also factor out an 8 at this point, but it's not going to be that helpful. So we'll just integrate as usual. From here, we can then just directly integrate this. It's simple enough. This gives us 8 theta minus, and again, the derivative of what is equal to just cosine. Derivative of sine is equal to cosine, so 8 over 3 sine theta. I'm realizing we didn't need square brackets, but it's fine. And we're evaluating this now at 0 and 2 pi. Yes. So this, again, similar idea. When we plug in 0 over here, it's not going to matter because we have 8 times 0 and then 8 over 3 times 0 because sine of 0 is 0. So we'll just focus on the 2 pi case. So we have 8 times 2 pi minus 8 over 3. Sine of 2 pi, again, is also 0, so times 0. And we just get 16 pi, just like that. I'll rewrite this a bit. For this, you don't really need to write a conclusion, but you can just say, like, therefore, the volume is 16 pi. You can say units cubed. Of course, they didn't even give you a unit, so you don't really need this, but that's if you do want to include an answer statement. Okay. Number 6, consider the iterated integral. I'm not going to read that out, but you can see it for yourself there. We want to sketch the region of integration. We want to label our axes and identify any points of interest. Okay, so first I will draw out an axis. And I'll label it, so x and y. This is not like high school where they'll get very specific and kind of, I don't know a great term to describe it, but if you don't like label a point, for example, they're not gonna take a mark off as long as you kind of indicate it and make it clear that you know what's going on. So in this case, we now want to pay attention to the limits of integration, but also with respect to what variable. So we know that with this current setup, we have x with this outside here. So x is between 0 and 2. 0 and 2, yes, so here I'll just write out to 4 with each direction, but you don't need it all. So 1, 2, 3, 4, 1, 2, I feel like these are not spaced well enough, 2, 3, then 4. So again, we know x is between 0 and 2, so I'll draw dotted lines roughly. Okay, we'll draw them a bit to the right. Still off a bit, eh? Good enough. Okay, and then for y, we know it goes between 4 and 2x. So 4 is constant, so we can kind of draw up here. And then 2x, we can also sketch out. So this goes from here all the way to this exact point over here. So if you were to label it, you could label this as 2, 4. And this is where now we want to, so this is just a region, of course, and we now also have to determine what the region is. Sorry, I should mention that. So this is where you need to be careful. So we know already that x is between 0 and 2, but of course, if we don't fully understand how the regions are determined, it's ambiguous. It could be this down over here, or it could be over here. But if we pay attention to the integration limits for y over here, we know that the lower bound is y is equal to 2x, so this line, and the upper bound is y is equal to 4, meaning our region is this over here. So I'll just color it in green. That right there is our region of integration. Now I'll just write this here, y is equal to 2x. And then obviously, the whole point of this question is to evaluate this integral, and the reason why they even have you sketch out the region is because you can change the order of integration. This right over here, there is no elementary derivative or elementary antiderivative for this. This plus 1 causes a lot of issues, or there may be one. Regardless, it's not feasible to do just directly with the current setup. You need to change your order of integration. So let's look into that. Okay, so write the region D as a different region. So I'll just write the region up over here. And again, I can use my, oops, that's too big. This one, yes, this one. So we know our region D is equal to, so here we just have points x comma y. Previously we had this right over here. I'm going to write out the new region of integration. So instead of x going between 0 and 2, we're going to go this way instead. So we're going from effectively a type 1 region to a type 2 region, I believe. So type 1 regions are where x is bounded between two constants and y is bounded between functions of x, and then vice versa for type 2. So in this case, we know that instead now we know y is bounded between right over here, so 0 and 4. 0 less than or equal to y less than or equal to 4. X, on the other hand, we need to then figure out how to bound x now. So x goes from left to right. So this is again for type 1, where we go from bottom to top. For whenever we're doing a type 2 region, it's left to right now. So we know that here we're bounded by x is equal to 0. And on the right, we're bounded between this now. So this right here is still the same function, but we need this in terms of x, which is simply just x is equal to 1/2 y. And 1/2 y, just like that. So this is the region that we're going to integrate over instead, which I will copy down over here. And then now we can proceed. So again, we have the double integral over just a region D, which is again the one up here, but we can then write it as an iterated integral. And the function we're integrating is y over y cubed plus 1 and dA. And then this is where we can now use our new type 2 region. Okay. So you have the integral. Okay. So here, again, instead of integrating in the order that we have here of dy dx, we're going to go dx dy, and you'll see why. Again, lots of why. You see why we do that in a sec. So again, our outside integration order is dy dx dy. So y is on the outside, so we have 0 and 4 here. And then x is between 0 and 1/2 y. Okay, and then same function, so y over y cubed plus 1. And then not dA anymore, so in this case, dx dy. The previous issue was in here you had to directly integrate this. Now when we change the order of integration, you can see what happens. We're integrating with respect to x, meaning this right here is just a constant, so we just multiply by x instead, which is very helpful. So integral 0 to 4. And now again, this right over here just moves out, so you have y over y cubed plus 1. But here we're multiplying by x now, because again, this is just a constant. You integrate 1, you just get x, and this is evaluated at x is equal to 0, and x is equal to 1/2 y. dy, dy. Okay, and then from here, we plug in 1/2 y over here, so we can pull out the 1/2. And then we multiply this by y. So we then get y squared between 0 and 4. We have y squared over y cubed plus 1. And then dy. But notice that this is actually something we are able to integrate now with a quick u substitution. So I'll write it out the full way. Usually what I do is I'll simply just do the u substitution in my head and then not change like the order of not the order of integration, but the limits. But I'll do it the kind of more formal or complete way. So our u sub is as follows. So u is going to equal to y cubed plus 1. Du is then 3y squared dy. And then in this case now, we notice that if we do substitute this in, we'll get something like 1 over u. And I'll show you why that's the case. And then here we also do need to consider what happens to our limits. So as y approaches 0, we can see what u approaches. So u approaches 1. And then as y approaches, y approaches 4, we have that u then approaches, so 4 cubed, 4 times 4 is 16, so 64 plus 1, so 65. And then we can write this down. So here, notice that we have the y squared dy, but we're missing this 3. You can either divide this over, and then just have that equality of 1 over 3 du, but again, pretty much up to preference. So in this case, what I like to think of is I'm going to multiply a 3 here, and then obviously we have to divide by 3 on the outside, same thing as multiplying by 1 over 3. And then this effectively is the same thing as multiplying by 1, but this does then give us the 3y squared dy, which allows us to do our u substitution. So we have 1 over 2 times 1 over 3. Now our limits of integration do change to u. So we have 1 and then 65. Top just becomes 1. Bottom here, we just have, that's actually much bigger than we need, sorry. So 1 over u du. So we have 1 over 6 times ln, again, the derivative of what is equal to 1 over u, it's the ln of u. So ln u evaluated, or I guess you could put absolute values, or ln of the absolute value of u, but it doesn't really matter in this case. Ln u evaluated at u is equal to 1, u is equal to 65. So you then have 1 over 6 times ln of 65 minus ln of 1. But of course, ln of 1 is just equal to 0, so you are left with ln of 65 over 6. So again, the main takeaway from this problem is you need to change the order of integration, because with the current setup here, it's just not going to happen. Okay, next, we want to calculate the double integral over here, where again, D is the region to the right of the y-axis bounded by this polar curve over here. So what I'll do is I'll quickly sketch this out. So we have 1 minus sign, so we're basically shifting up negative sign up by 1. So this will become kind of like our middle. So this is again r theta. And then, yeah, we're only looking for one revolution, so 2 pi, so we'll have pi over 4, or not pi over 4, let's go pi over 2, pi, 3 pi over 2, and then 2 pi. And then again, we know that this roughly looks something like this. Yeah, definitely butchered that, but you get the idea, something like this. If you don't already immediately recognize to be a cardioid, definitely look into polar curve sketching a lot more, but hopefully you do recognize that this is a cardioid. Even if you don't, we'll quickly sketch it over here. So when you're starting at theta is equal to 0, we start at 1. Notice that our radius is decreasing as we approach pi over 2, so as we approach this vertical part here. So it looks something like this. And then from pi over 2 to pi, we know that we continue to increase again. So this is all positive, which is more convenient for sketching. And then after we hit pi, which is over here, or pi over here, we then again reach 1. So we should get over here. And hopefully you see the cardioid shape taking shape now. And then at 3 pi over 2, we hit 2, which is somewhere down over here. And then when we hit back to 2 pi, we're back to 1. So back to this. Mine is more kind of squished down, but it gives you the general shape or the idea. So now we're again looking for the region, again D. It's bounded to the right, sorry, it's to the right of the y-axis bounded by this polar curve. So this is what we're looking for right over here. Okay, and we can now express this using D. I'll use my thing over here. Okay, so clearly we definitely do need to use polar coordinates, so our theta. Here's where we have to be a bit careful. Remember, when we're calculating, are we calculating volume? Okay, well, we're not even calculating volume, but regardless, we're trying to represent this region over here. And this region, it can't be represented if you just use 0 to 2 pi. In this case, we start at 3 pi over 2, and then we have to eventually go kind of all the way up here. Right over here, this is 5 pi over 2. And then, so with that, yeah. So we have 0, that's equal to theta. Or sorry, not 0, sorry. So again, we need to start here at 3 pi over 2. And then we need to work our way back up here, which becomes 5 pi over 2. So just 2 pi plus pi over 2. So 3 pi over 2, theta, and then 5 pi over 2. And then our radius, this is where it becomes a little different. Again, remember, whenever we're bounded by a polar curve, our radius will usually always be between 0 and whatever that polar curve is. So 0 is less than or equal to r, less than or equal to 1 minus sine theta. And then we can move this back up here now. So this is, again, the region we're integrating over, and then we're still integrating this function. So let's get into that. So we have the integral, the double integral, over the region D of x dA. And then now we can plug in these values over here and write it as an iterated integral, but again, remember, in polar coordinates. So we have the integral over here. So again, r dr d theta, theta is on the outside, so 3 pi over 2. And then 5 pi over 2. Our radius r goes between 0 and 1 minus sine theta. And then x, again, remember, because we're dealing with polar coordinates, it's r cos theta. and then times r dr d theta. From here, we can evaluate as normal. So here we have r squared. Again, it becomes r squared cos theta. If we integrate that with respect to r, it becomes 1/3 r cubed. So let's write that out here. So 3 pi over 2, 5 pi over 2. And then again, 1/3 r cubed cos theta. Evaluated at r is equal to 0 and r is equal to 1 minus sine theta d theta. So of course, if we use r is equal to 0 over here, or we have 1 minus sine theta, and then minus 0, obviously in this cubed, obviously this just remains this. So then we can rewrite this. So I'll drag out the 1/3, move it out. And then we have the integral from 3 pi over 2 to 5 pi over 2. And then we have 1 minus sine theta cubed times cos theta d theta. Okay, I'm going to pause really quickly. This step is where you really want to be careful. I was stupid enough to expand this out and then integrate from there. I still got it right, but that was way longer than it needed to be. In this case, if you recognize that you can do a u substitution, you'll save so much time. So we'll do that over here. So u, we can substitute for 1 minus sine theta. And then obviously du then becomes negative cos theta. And then now we can consider the limits of integration. So as theta approaches 3 pi over 2, we see that u, so 3 pi over 2, sine 3 pi over 2 is down here, gives you that -1. So you have 1 minus -1, excuse me, 1 minus -1, so u approaches 2. And then when theta approaches 5 pi over 2, we have that u approaches. So 5 pi over 2 is, again, equivalent to just pi over 2 in terms of the value of sine. So sine 90, or sine pi over 2, is 0. So approaches to 1, I believe. Or sine, oh, sorry, 1 minus, yeah. So 1 minus 0, so just, or sine, oh, sorry, sine 90 is 1. So sine of pi over 2 up over here is positive 1. So 1 minus 1 is 0. And these are the limits of integration now. So here, we can write this as 1 over 3 times the integral. Again, now we're going between 2 and 0. So it does look a bit weird that it is kind of backwards, but that's fine. It'll work out. 1 minus sine theta is our u. So we effectively just have u cubed. And then negative cos theta, we need to kind of force. So we can multiply by a negative out here. Think about it this way. We multiply by a -1 here effectively, and we also multiply by a -1 there. So it effectively becomes like just multiplying by 1 or not changing anything. So that cos theta, negative cos theta d theta just becomes r du. And now we can integrate as we normally do. So negative 1 over 3 times 1 over 4 u to the power 4. And again, we're evaluating this at u is equal to 2 and u is equal to 0. So of course you can stay within just r and theta values when integrating, but this I also find to be just, it works just as fine. So then we can move out this 1 over 4, so we have negative 1 over 12. 0 to the power 4 is just 0, and then 2 to the power 4 is 16. 2 times 2, 4, 8, 16. So minus 16. And then obviously the negatives cancel out. You have 16 over 12, which then reduces to 4 over 3. And that right there is how you would integrate this. So definitely do not make the mistake I made, which is expanding this. Whenever you see something like this, think for a second, see if there's a better way to do it. In this case, a u substitution saves you a lot of time. But yeah, perfect. Thank you for watching.